There are moments in science when the universe whispers, and then there are moments when it shouts. On July 1st, 2025, a telescope in Chile captured something that would challenge everything we thought we understood about comets, physics, and perhaps even our place in the cosmos. An object was racing toward our sun at 130,000 miles per hour, traveling backward through space, defying the choreography of the planets. They named it 3I/Atlas, the third interstellar visitor we've ever caught in the act of passing through. But this visitor refuses to follow the script. Have you ever wondered what happens when an object from beyond our solar system arrives carrying signatures that don't match anything in nature? When Harvard astrophysicist AviLoeb examined the data, he ranked it a 4 on his scale of technological probability, where 0 means definitely natural and 10 means definitely artificial. 4 sits in the uncomfortable middle, the place where science must confront possibilities it wasn't prepared to consider. Tonight, we're going to walk through 9 specific ways that 3I/Atlas breaks the fundamental rules that govern every comet we've ever studied. 9 anomalies so profound that they've triggered NASA's planetary defense protocols, mobilized international monitoring networks, and sparked the most intense scientific debate in modern astronomy. And as we examine each one, you'll see why this distant traveler has forced us to ask a question that seemed like science fiction just months ago. What if some objects in space don't follow our laws because they were never meant to? The answers are coming. The data is arriving in real time. And by the time this visitor completes its passage through our solar system, we may need to rewrite entire chapters of what we thought we knew about the universe. Let's begin with something that should be impossible. Anomaly 1. The mass that doesn't make sense. Picture a chunk of rock and ice 5 kilometers across. That's about 3 miles, roughly the length of Manhattan from Battery Park to Central Park. Now imagine that chunk weighs at least 33 billion tons. That's the minimum mass of 3I/Atlas, calculated from observations spanning months, compiled from over 4,000 data points, collected by 227 observatories worldwide. 33 billion tons. Let that sink in for a moment. To put this in perspective, the previous interstellar comet we discovered, 2I/Borisov, was about 1 kilometer across, is 1,000 times more massive. 1,000 times. It's moving faster than both previous interstellar visitors combined. The probability of finding an object this massive and this fast, arriving precisely when it did, less than 0.1%. But here's where the physics breaks down. When comets approach the sun, they shed material. Ice sublimates, gas erupts from the surface, and this outgassing creates a rocket effect. It's subtle, but it's measurable. Every comet we've ever studied shows non-gravitational acceleration from this process. It's as reliable as sunrise. 3I/Atlas showed almost none. Between May and September of 2025, astronomers tracked its motion with extraordinary precision. The deviation from a purely gravitational trajectory? Less than 0.028 arc seconds. That's like trying to spot a human hair from 1 kilometer away. The non-gravitational acceleration was smaller than 15 meters per day squared, for a comet losing 150 kilograms of material every single second. With gas streaming away at 440 meters per second, this silence is deafening. The only way to explain this lack of rocket effect is if the object is extraordinarily massive, far more massive than its size suggests. Either the material inside is incredibly dense, denser than we'd expect for a natural comet, or something else is stabilizing its trajectory, in ways we don't understand. Richard Cloet, who co-authored the paper calculating this mass, noted that this creates a statistical problem. Given the limited reservoir of heavy elements ejected from dying planetary systems across the galaxy, we should have discovered roughly 100,000 smaller interstellar objects before ever finding something like 3I Atlas. Yet we've only detected 2 others. The universe doesn't usually hide its small rocks while showing us the boulders. Unless, of course, there's a reason this particular boulder wanted to be seen. Can you imagine an object so precisely balanced that it absorbs the force of erupting gas without changing course? What would need to be inside to create such stability? Anomaly 2. Traveling against traffic. Think of our solar system as a cosmic roundabout. The planets orbit the sun in one direction, like cars circling clockwise around a traffic circle. Most objects that form within our system follow this same pattern because they condensed from the same rotating disk of gas and dust that birthed the sun. Now imagine a car entering that roundabout, traveling at highway speed in the opposite direction. That's 3I Atlas. It's moving in retrograde motion, backward relative to the planets, yet somehow remaining aligned with the flat plane of the solar system. This combination should be extraordinarily rare for an interstellar object, which should arrive from random directions in 3-dimensional space. The probability of an interstellar visitor aligning so closely with our solar system's ecliptic plane while traveling retrograde? Astronomers calculate it at a fraction of a percent. This alignment isn't just unusual, it's geometrically suspicious. Objects in bound orbits around the sun can gradually evolve into retrograde paths through gravitational interactions over millions of years. But 3I Atlas isn't bound. It's on a hyperbolic trajectory, meaning it's moving too fast for the sun's gravity to capture it. It entered our solar system already traveling this way, already aligned, already moving against the cosmic current. When you plot the incoming velocity vector in galactic coordinates, 3I Atlas shows a vertical W velocity of plus 18.5 kilometers per second relative to the sun. That's unusually high compared to nearby stars and other interstellar objects. It means this visitor is moving through the galaxy on a tilted orbit, belonging to either the thin disk or thick disk populations of our Milky Way. If it came from the thick disk, a region populated by ancient stars whose compositions contain fewer heavy elements than our sun, then 3I Atlas could be 7 to 14 billion years old. That would make it older than Earth, older than our solar system, older than most of the planets orbiting most of the stars you can see in the night sky. An object that old, traveling that precisely, arriving now. The geometry suggests either remarkable coincidence or remarkable intention. And science has a rule about coincidences. When they pile up, start looking for patterns. What would you do if you wanted to visit a solar system you'd never seen before? Would you approach randomly, or would you follow the traffic patterns, staying in the plane where the planets live, where life is most likely to emerge? Anomaly 3. The sunward jet. That shouldn't exist. On July 21, 2025, the Hubble Space Telescope captured something that made astronomers pause mid-coffee. A jet of material was streaming from 3I Atlas, but it was pointing the wrong direction. Comet tails always point away from the sun. This is fundamental physics, taught in every introductory astronomy course. Solar radiation pressure and the solar wind, that constant stream of charged particles erupting from our star, push gas and dust away from the sun's direction. It's as reliable as gravity itself. 3I Atlas developed a sunward jet, an anti-tail. Now, before you dismiss this as an optical illusion, understand that astronomers checked. They analyzed the geometry from multiple angles, examined the projection effects that can sometimes make tails appear to point in unusual directions. This wasn't a perspective trick. Material was genuinely streaming toward the sun, against the flow of radiation and solar wind that should have been pushing it away. The Nordic Optical Telescope tracked this behavior through July and September, watching the dust fan shift from its normal anti-solar configuration to this bizarre sunward orientation. The particle dynamics required to explain this naturally become tortured, requiring special pleading about magnetic fields, asymmetrical jets, and unusual gas compositions. But here's what makes this particularly troubling. NASA's initial public communications about 3I Atlas omitted this detail entirely. The Hubble images showed it clearly. The data was published in scientific papers. Yet the agency's blog posts describing the object as a simple interstellar comet somehow forgot to mention that the comet was behaving in fundamentally non-comet-like ways. The sunward jet appeared early in the observation campaign, long before 3I Atlas reached its closest approach to the sun. It wasn't a brief anomaly or a measurement error. Multiple observatories confirmed it over weeks. And when you combine this with the other anomalies we're discussing, a pattern begins to emerge. Jets of material can be used for propulsion. If you can direct where the gas goes, you can push yourself in the opposite direction. It's basic rocket science. Natural comets develop jets, but those jets are random, chaotic, determined by where the sun happens to heat the surface and where weak spots exist in the icy crust. A sunward jet, sustained over time, requires explaining why material would consistently erupt from the sun-facing side and direct itself inward. Unless, of course, you wanted to accelerate away from the sun while appearing to be a comet. Then a sunward jet would be exactly what you'd expect to see. Have you considered what it means when nature breaks its own rules in ways that look suspiciously like engineering? Anomaly 4. The nickel without iron. Mystery chemistry tells stories. The elements present in an object and their relative abundances reveal where that object formed and what processes shaped it. Comets from our solar system have signatures as distinctive as fingerprints, built from the primordial soup that condensed into our sun and planets 4.6 billion years ago. On August 24th, 2025, the Keck Observatory in Hawaii aimed its powerful spectrograph at 3I Atlas and found something that shouldn't exist in nature: prominent nickel emission without accompanying iron. Let me explain why this matters. Nickel and iron are cosmic siblings, forged together in the cores of massive stars and scattered across space when those stars explode as supernovas. They occur together everywhere in the universe because they're created by the same nuclear processes. When you find nickel in cosmic objects, you find iron in roughly the same proportions, always, except in 3I Atlas. The spectral analysis showed nickel vapor, atomic nickel glowing in the ultraviolet, at concentrations that should have been accompanied by iron signatures. But the iron was either absent or so weak as to be nearly undetectable. The nickel to cyanide ratio was orders of magnitude larger than any known comet, including 2I Borisov, the previous interstellar visitor we studied in detail. On Earth, there's exactly one process that produces nickel without iron: industrial refining. We separate nickel from iron ore because pure nickel alloys have properties that iron-nickel mixtures don't. Nickel alloys are stronger, more resistant to corrosion, better suited for high-stress applications, and they're produced deliberately through metallurgy. But we're not on Earth. We're looking at an object that formed billions of years ago, potentially in a solar system hundreds of light years away. Natural processes should dominate completely. So where did the iron go? The mystery deepens when you consider temperature. Nickel has a high vaporization point. It doesn't easily turn into gas. Yet observers detected nickel vapor at extreme distances from the sun, where temperatures should be far too cold for metals to sublimate naturally. The sun's heat alone cannot explain vaporized nickel at those locations and temperatures. There's a compound called nickel tetracarbonyl that can form when nickel reacts with carbon monoxide at relatively cool temperatures. It's one of the few volatile nickel compounds that exists. Interestingly, it's also used in industrial processes for purifying nickel and depositing nickel coatings. It was discovered in industrial settings, and it remains associated with metallurgical applications. If nickel tetracarbonyl is present in 3I Atlas, it would explain how nickel vapor appears at cold temperatures. But it wouldn't explain why this particular compound, this particular chemistry, exists in an object that's supposedly a pristine remnant from another star system. The probability of this specific chemistry emerging naturally, in these specific proportions, from natural cometary processes, less than 1%. When rocks from space show signatures we only create in factories, what conclusion should we draw? Anomaly 5. Carbon dioxide dominance and the missing water. Every comet we've studied from our solar system is fundamentally made of dirty ice. Water ice forms the bulk of the volatile material, mixed with dust, rocks, and frozen gases like carbon dioxide and carbon monoxide. When you measure the spectral signature of a typical comet, water dominates overwhelmingly. The James Webb Space Telescope turned its infrared eye toward 3I Atlas on August 6, 2025, and discovered something strange. The comet is unusually rich in carbon dioxide while containing only small amounts of water ice and water vapor. This inversion shouldn't happen. Water is one of the most abundant molecules in the universe. It forms readily in the cold regions of space where comets are born. The ratio of water to carbon dioxide in typical solar system comets runs heavily toward water, sometimes by factors of 10 or more. Finding a comet where carbon dioxide rules suggests formation in an environment with very different chemical conditions than anything in our neighborhood. The spectroscopic observations revealed carbon dioxide concentrations, along with small amounts of carbon monoxide and carbonyl sulfide. The water that typically dominates cometary spectra was present but subdued. This chemical fingerprint suggests either formation around a very different type of star with different temperatures and chemical abundances, or processing that removed water preferentially while leaving carbon dioxide behind. Removing water from ice while preserving other volatiles isn't something nature does easily. Water is stable, tenacious. It sticks around. Getting rid of it while keeping carbon dioxide requires specific conditions that are hard to achieve naturally, but relatively straightforward to engineer. The implications ripple outward. If 3I Atlas formed in a star system with chemistry this different from ours, it tells us something profound about the diversity of planetary systems in the galaxy. But it also raises questions about the object's trajectory and timing. Why would a comet from such an exotic origin arrive now, travel through our system at this speed follow this particular path. The carbon dioxide also offers a clue about age. In the cold regions of interstellar space, ice accumulates over millions of years. The ratio of different ice types preserves information about the conditions when they froze. If 3I Atlas has been wandering the galaxy for 7 to 14 billion years, as some estimates suggest, its ice should show signatures of that vast journey. And carbon dioxide-rich ice could be exactly what you'd expect from an object born when the galaxy was younger, when stars had different chemical compositions. But carbon dioxide also has another property. It sublimates at lower temperatures than water. If you needed to design a propulsion system that used sublimating gas to generate thrust, carbon dioxide would be a more efficient choice than water. It turns to gas earlier, responds more predictably to temperature changes, and requires less energy to activate. Every time we peel back another layer of 3I Atlas, we find chemistry that could be explained naturally with sufficient creativity, or could be explained simply if we allow for different assumptions about origin. How many times can coincidence stack before pattern emerges? Anomaly 6. The timing and trajectory miracle. Imagine throwing a paper airplane from the top of a skyscraper in New York City and having it land in a specific coffee cup on a specific table at a specific cafe in Los Angeles. Now imagine it happens without you having any idea where Los Angeles is, how far away it is, or what a cafe looks like. That's approximately the level of geometric precision required for 3I Atlas's trajectory. This object arrived in our solar system on a path that brought it within tens of millions of kilometers of Mars, Venus, and Jupiter, while rendering it completely unobservable from Earth during its closest approach to the Sun. The probability of an interstellar visitor arriving with this specific alignment, this specific timing, threading the needle between multiple planets while coinciding with a natural observational blind spot, 0.005%, 0.5% of 1%. On October 29th, 2025, 3I Atlas reached perihelion, its closest point to the Sun. At that exact moment, the Sun's glare made ground-based observation impossible. The period from October 8th through October 18th created a blackout window when conventional telescopes couldn't track the object. This wasn't planned by astronomers. It's a consequence of orbital geometry and the Sun's position relative to Earth. But here's what makes this timing remarkable. The most interesting things happen during the blackout. The closest solar approach, any potential changes in behavior near peak heating, possible outbursts or fragmentations all occurred when official observation was constrained. It's as if someone scheduled an important meeting during lunch hour, knowing everyone would be away from their desks. The trajectory also brought 3I Atlas close to Mars on October 3rd, close enough that the Mars Reconnaissance Orbiter's high-rise camera could image the object with resolution around 30 kilometers per pixel. These images could have provided crucial data about the object's size, shape, and behavior. They were taken as scheduled, but as of early November, those images haven't been released to the scientific community. NASA cited the government shutdown in October as the reason for delayed data release. But amateur astronomers noted that the HiRISE team continued posting archival images during this period. The images exist. The data has been captured. It simply hasn't been made public. Meanwhile, on December 19th, 2025, 3I Atlas will pass closest to Earth, at a distance of 269 million kilometers. That's still quite distant, but close enough for hundreds of ground-based telescopes, along with Hubble and Webb, to observe it in unprecedented detail. This will be the moment of truth, when the accumulated questions might finally receive answers. The international scientific community is preparing. Between November 27th and January 27th, 2026, the International Asteroid Warning Network has scheduled a coordinated observation campaign. Not because 3I Atlas poses a threat. The object will pass harmlessly through our solar system and continue into interstellar space. The campaign is scheduled because the International Asteroid Warning Network uses interesting objects as training exercises for planetary defense, and because the scientific community wants every possible data point this visitor can provide. But the timing remains troubling. An object that old, that massive, that unusual in composition and behavior, arriving precisely when it can thread between planets, hide during its most active phase, and generate maximum scientific controversy. Either we're witnessing the most remarkable series of coincidences in modern astronomy, or something about this object's trajectory was deliberate. When does careful planning become indistinguishable from luck? Anomaly 7. The blue brightening that broke models between late October and early November 2025. As 3I Atlas approached and passed perihelion, something unprecedented happened. The object brightened dramatically, increasing in luminosity while simultaneously turning blue. Bluer than the sun. Comets don't do this. When comets approach the sun and heat up, they brighten because they're releasing more gas and dust, which scatters sunlight. But the color of that scattered light depends on the composition of the dust and the temperature of the gas. Natural cometary outgassing produces colors ranging from white to yellow to reddish, depending on the organic compounds and minerals present. Blue light indicates high energy. It means something is happening that requires more energy than simple ice sublimation can provide. It suggests ionization, plasma formation, or chemical processes that operate at temperatures higher than cometary surfaces, should reach at 1.36 astronomical units from the Sun. The observations came from multiple solar observatories that could track 3I Atlas during the period when Earth-based telescopes were blocked by solar glare. Zhang and Batoms, using this solar observatory data, confirmed what looked like violent acceleration with a scaling factor of r to the negative 7.5 power. That's a mathematical description of how rapidly the acceleration decreased with distance from the Sun, and it's far steeper than natural cometary outgassing should produce. The acceleration rate measured approximately 60 kilometers per day, squared in the transverse direction, perpendicular to the Sun-comet line. Natural outgassing should produce acceleration primarily in the radial direction, either toward or away from the Sun, because that's the direction of temperature gradients. Transverse acceleration, the kind that changes an object's trajectory sideways, requires jets oriented in very specific directions. AviLoeb calculated that to produce this level of non-gravitational acceleration through natural outgassing, 3I Atlas would need to lose at least 1/6 of its total mass. That's a staggering amount of material. If the object shed that much mass during perihelion, it should be surrounded by a massive, detectable cloud of gas and dust in November and December, when post-perihelion observations become possible. Here's the prediction that will either vindicate or refute the exotic explanations. If 3I Atlas lost 1/6 of its mass through natural outgassing, we should see that gas cloud clearly when observation resumes. If we don't see a massive gas envelope surrounding the object, then cometary evaporation cannot explain the observed acceleration. And if cometary evaporation can't explain it, we'll need a different mechanism. That mechanism would need to generate thrust, change velocity, and do so in ways that produce blue light and high-energy signatures. Rocket engines fit that description. So do certain types of electromagnetic propulsion systems. Natural processes struggle to match the requirements. The blue color itself remains unexplained. Cometary comas sometimes show blue emissions from ionized molecules, but not at the wavelengths and intensities observed. The physics behind this coloration, as one researcher noted, is something we need to understand. We haven't had time to figure out the physics behind it. The December observations will be crucial. They'll reveal whether the predicted gas cloud exists, whether the blue coloration persists, and whether the acceleration measured during perihelion was a transient event or part of a consistent pattern. The data won't care about our theories. It will simply show what happened. And if what happened doesn't match any natural model we've constructed, then we'll need to consider what that means. Anomaly 8. The silence of missing data science advances through transparency. Observations are made, data is collected, findings are published, and the community evaluates evidence collectively. When information flows freely, truth emerges from the competition of ideas and the scrutiny of evidence. But what happens when key data disappears into institutional silence? The high-rise images from October 2nd and 3rd could have resolved crucial questions about 3I Atlas. The Mars Reconnaissance Orbiter's camera has the highest resolution of any instrument that could capture a sideways perspective of the object. From that angle, transverse acceleration could be separated from rotational effects. The source of any jets or emissions could be isolated geometrically. The object's true size and shape could be determined with unprecedented precision. These images were taken. They exist in NASA's archives, but they haven't been released. When Congresswoman Anna Paulina Luna inquired about the images, she was told the October government shutdown had delayed processing and release. Fair enough. Shutdowns affect operations. But the timing created a vacuum at a critical moment when scientific debate was intensifying, when extraordinary claims were being made, and when definitive observational data could have settled key questions. The delay, whether intentional or bureaucratic, had a consequence. It preserved ambiguity. Without the geometric constraints that high-rise images would provide, advocates of the simple Comet model could maintain that all anomalies result from projection effects, rotational artifacts, or measurement errors. Without the images, debate continues. With the images, certain possibilities would be excluded. This isn't the only information gap. NASA's official communications about 3I Atlas have been curiously selective. The agency's blog posts describe the object as an interstellar comet, which is accurate, but they omit discussion of the specific anomalies that make this particular comet unlike any other. The sunward jet isn't mentioned. The nickel without iron signature isn't discussed. The unusual trajectory alignment doesn't appear. On October 30th, as perihelion passed, NASA Administrator Bill Nelson issued a statement on social media. No aliens, no threat. The message was brief, definitive, and unaccompanied by any discussion of the scientific anomalies that had prompted speculation in the first place. Compare this to the level of detail NASA typically provides when discussing unusual objects. The agency excels at science communication, offering rich explanations of phenomena, detailed technical breakdowns, and transparent sharing of data. The selective briefness regarding 3I Atlas stands in contrast. Independent researchers like AviLoeb have published 11 scientific papers about 3I Atlas in recent months, detailing anomalies and analyzing data. These papers are peer-reviewed, publicly accessible, and specific about what makes this object unusual. Yet institutional responses have been abbreviated, focusing on reassurance rather than engagement with the anomalies. The silence isn't just about missing images. It's about a pattern of delayed information, selective communication, and institutional caution that contrasts sharply with the transparency usually characterizing space science. And in that silence, speculation flourishes. Without data to settle questions definitively, every interpretation remains possible. The coming weeks will test whether this silence was simply bureaucratic delay or something more deliberate. As the International Asteroid Warning Network's coordinated observation campaign proceeds, as December brings the object closest to Earth, as ESA's JUICE mission and NASA's Juno spacecraft contribute their observations, the flood of data will either drown the exotic theories in natural explanations or substantiate them beyond reasonable doubt. But the questions raised by missing data matter, regardless of what that data eventually shows. When institutions choose discretion over transparency, when image release is delayed at critical moments, when simple explanations omit complicated details, trust erodes. And in the search for truth about objects like 3I Atlas, trust in the process is as important as the data itself. Anomaly 9. The statistical impossibility of everything together. Perhaps the most powerful argument about 3I Atlas isn't any single anomaly. It's the compound probability of all anomalies occurring in the same object. Think of it like this. Finding a person who's 7 feet tall is rare. Finding a person who's 7 feet tall and left-handed is rarer. Finding a person who's 7 feet tall, left-handed, and born on February 29th is rarer still. Each additional unlikely characteristic multiplies the improbability. 3I Atlas is 7 feet tall, left-handed, born on leap day, has perfect pitch, knows ancient Sanskrit, and won the lottery twice. Let's stack the probabilities. The object is anomalously massive and large compared to the population of interstellar objects we should expect to discover. Probability, less than 0.1%. It arrived with timing that brought it close to multiple planets while creating an observational blind spot at perihelion. Probability, 0.005%. It travels in retrograde motion while aligned with the ecliptic plane, a combination unlikely for random interstellar arrivals. Probability, less than 1%. Its chemical composition shows nickel without accompanying iron, and carbon dioxide dominating over water, both deviations from known cometary norms. Combined probability for these specific chemistry anomalies, less than 1%. It displayed a sunward jet, blue brightening, and non-gravitational acceleration patterns inconsistent with normal cometary behavior. Individual probabilities for each, uncertain but low. When you multiply these independent probabilities together, you reach numbers so small they become difficult to conceptualize. The compound probability of all these anomalies co-occurring in a single natural object approaches the mathematically negligible. This is why AviLoeb assigned 3I Atlas a rank of 4 on his scale of technological probability. Not because any single anomaly proves artificiality, but because the combination of anomalies creates a burden of proof that natural explanations struggle to meet. Science operates through Bayesian reasoning, where we update our probability estimates as new evidence arrives. Before 3I Atlas, the prior probability of an artificial interstellar object visiting our solar system was considered extraordinarily low, but Bayesian reasoning says we must update that prior based on observations. Each anomaly shifts the probability, and when anomalies accumulate beyond a threshold, even a very low prior can be overcome by sufficiently unlikely observations under the natural hypothesis. The critical question becomes, at what point do natural explanations become more contrived than technological ones? When we need to invoke multiple rare processes, each operating at the edge of known physics, each required to explain a different aspect of the same object, all coincidentally occurring together, we should ask whether we're protecting a conclusion rather than following the data. The December observations will matter enormously. They'll either reveal the massive gas cloud that cometary evaporation requires to explain perihelion acceleration, or they won't. They'll either show continued anomalous behavior, or they'll show the object settling into conventional cometary patterns. They'll either force us to invent new natural processes to preserve conventional interpretations, or they'll confirm that existing natural processes suffice. But whatever the observations show, this much is already clear. 3I Atlas has pushed our understanding of cometary physics to its absolute limits. Every anomaly has an edge case natural explanation if we stretch hard enough. But when every characteristic requires an edge case, when nothing about the object follows typical patterns, when the compound probability drops below thresholds we normally consider decisive, then we must at least entertain the possibility that our fundamental assumptions about this object might be wrong. Have we created a prison of certainty for ourselves, where even evidence that screams for reconsideration gets muffled by institutional inertia and the fear of appearing foolish? The witness period. What happens next? We are living through a unique moment in scientific history. 3I Atlas is passing through our solar system right now. The observations are happening in real time. The data that will answer these questions is being collected as you hear these words. December 19th, 2025, marks the closest Earth approach. On that day, 3I Atlas will be 269 million kilometers away, still distant, but within optimal range for our most powerful instruments. Hundreds of telescopes will be pointed at this object simultaneously. Hubble will capture high-resolution images. Webb will dissect its spectral signature with unprecedented precision. Ground-based observatories across every continent will track its position, monitor its brightness, analyze its composition. The IIWN coordinated campaign runs from November 27th through January 27th, 2026. This isn't just about 3I Atlas specifically. It's a training exercise for planetary defense, testing international coordination, data sharing, and rapid analysis capabilities. But it means the object will receive more concentrated attention than perhaps any comet in history. What will we find? If 3I Atlas is a natural comet exhibiting unusual but explicable behavior, the December observations should reveal a massive gas envelope surrounding the nucleus, consistent with losing 1/6 of its total mass during perihelion passage. This gas cloud is required to explain the observed acceleration through rocket effects, continued but decreasing activity as the object moves away from the sun, following predictable patterns based on temperature and solar distance. No further evidence of transverse acceleration or unexplained trajectory changes. Chemical signatures that, while unusual, fit within the broad spectrum of cometary compositions observed in other systems. If these observations are made, the exotic theories will collapse under their own weight. Natural processes will suffice. The compound probability of anomalies will prove less meaningful than thought, and 3I Atlas will take its place as a fascinating but ultimately normal interstellar visitor, teaching us about the diversity of comets beyond our solar system. But if the observations show something different, no massive gas cloud or a gas envelope, insufficient to explain the observed acceleration through natural outgassing, continued anomalous behavior, including additional trajectory changes, or unexplained brightness variations, chemical or physical signatures that cannot be reconciled with natural cometary processes, even when allowing for formation in exotic stellar environments. Evidence of structure, organization, or patterns that suggest manufacture rather than accretion. Then we will face a conclusion that no one in authority wants to say out loud. We may be observing technology. The resistance to this conclusion is understandable. The history of false alarms and the search for extraterrestrial intelligence has made the scientific community wary. The social and philosophical implications of confirming artificial objects from other civilizations are profound enough that institutional caution is warranted. And the chance of being wrong, of becoming the generation that cried alien before absolute proof existed, creates powerful psychological barriers. But caution can become dogma. Skepticism can become denial. And the obligation of science is to follow evidence wherever it leads, even when it leads somewhere uncomfortable. AviLoeb has stated publicly that if the December observations don't reveal the predicted gas cloud, then cometary evaporation fails as an explanation for the perihelion acceleration, and technological signatures must be seriously considered. This is a falsifiable prediction. It will either be vindicated or refuted by direct observation. That's how science is supposed to work. Meanwhile, amateur astronomers and independent researchers have stepped into the gap created by institutional caution. Networks of backyard observers have coordinated observations, repurposed radio telescopes, adapted weather satellites. When official oversight was constrained during perihelion blackout, the citizen science community maintained watch. Their contributions will be crucial in the analysis to come. The democratization of observation matters here. The sky belongs to everyone. When professional astronomy encounters questions too controversial for comfortable discussion, amateur enthusiasts often possess both the tools and the freedom to ask uncomfortable questions and report what they see without institutional filtering. In the end, 3I Atlas will tell its own story. Objects can't lie. They simply are what they are. And in the coming weeks, as data accumulates, as observations build, as the picture sharpens into focus, we'll know. Whatever that knowledge reveals, will have grown. If 3I Atlas proves natural, we'll have expanded our understanding of cometary diversity, chemical possibilities, and the range of behaviors that objects from other stellar neighborhoods can exhibit. If it proves technological, we'll have confirmed the most profound truth in human history. We are not alone, and we never were. The long perspective. Stand outside tonight if the sky is clear and look up. Somewhere among those stars, 3I Atlas began its journey. Somewhere out there, perhaps 7 billion years ago, perhaps 14 billion years ago, this object formed. It has traveled through the galaxy for longer than complex life has existed on Earth. It has witnessed stars being born and dying. It has passed through nebulae, drifted through the emptiness between spiral arms, circled the galactic core dozens or hundreds of times. And in July 2025, human beings happened to notice it arriving. Think about that timeline. The first humans who could build fire lived 400,000 years ago. Written language emerged around 5,000 years ago. The telescope was invented in 1608. Modern astronomy, capable of detecting and tracking interstellar objects, is barely 2 decades old. The window of time when humanity possessed both the capability to see 3-eye atlas and the knowledge to recognize what we were seeing is measured in years. If this object is natural, its arrival now is purely coincidental. The galaxy is full of wandering comets, fragments ejected from dying planetary systems, ice balls drifting through the void. One happened to pass through our cosmic neighborhood during the brief moment when we could notice. If this object is not natural, its arrival now is precisely timed. It arrived when we could see it, when we could analyze it, when we could ask the right questions. And that timing implies either remarkable surveillance capabilities, monitoring our technological development, or pre-planning on timescales that dwarf human civilization. Either possibility reshapes how we think about cosmic time and cosmic purpose. For young people watching this, considering careers in science, engineering, astronomy, this is your moment. You are living through the unfolding of a mystery that will be discussed and analyzed for decades. The data being collected now will be pored over by researchers for years to come. The questions raised by 3-eye atlas will drive instrument design, observation strategies, and theoretical modeling for the next generation of space science. There will be PhDs written about this object. Careers will be built on analyzing its properties. New telescopes will be proposed specifically to catch the next interstellar visitor earlier, track it longer, and answer questions we couldn't answer about 3-eye atlas. The search for extraterrestrial technology will shift from radio signals to object detection, from listening for messages to looking for machines. And you could be part of that. You could be the engineer who designs the next generation spectrograph that captures chemical fingerprints with enough precision to distinguish industrial processes from natural ones. You could be the astronomer who develops the statistical methods for evaluating compound probabilities of anomalous characteristics. You could be the mission planner who proposes the first dedicated interstellar object interceptor, a spacecraft designed to rendezvous with visitors like 3-eye atlas, to observe them up close, to sample their material directly. The universe has handed your generation a puzzle. The previous interstellar object, Oumuamua, arrived and departed before we could study it adequately. 2-eye Borisov gave us more time, but still escaped before comprehensive analysis was complete. 3-eye Atlas is the third chance, and we're making the most of it. But there will be more. Statistical models suggest several interstellar objects pass through the inner solar system every year. We just haven't been looking carefully enough to find them. The Vera Rubin Observatory, coming online soon, will change that. Its wide-field survey capability and rapid cadence will detect interstellar visitors earlier, track them longer, and provide the data streams needed for real-time analysis. The next 3-eye atlas might be found months before perihelion, giving us time to reposition spacecraft, coordinate observations, even launch dedicated missions if the object warrants. We are building the infrastructure for interstellar object archaeology, studying visitors from other stellar systems to learn how planets form, how chemistry varies across the galaxy, and yes, to search for evidence of technology from civilizations that arose long before Earth even existed. This is the frontier. This is where discovery happens. This is where you belong, if the question calls to you. The question that won't go away. Have you been thinking about it as we've walked through these 9 anomalies, as we've examined the compound improbabilities, as we've seen the patterns that keep appearing in the data? Have you been asking yourself the question that everyone asks, but hesitates to say out loud? Could it be artificial? It's not a comfortable question. It carries baggage. It invites mockery from some quarters and overenthusiasm from others. It leads down paths that feel more like science fiction than science. And yet, the question persists because the data won't let it go. When natural explanations require stacking improbability on improbability, when every characteristic demands an edge case exception, when the compound probability drops below levels we'd accept in any other field of inquiry. At some point, intellectual honesty requires acknowledging the possibility, however unlikely our priors suggest it should be. This doesn't mean declaring 3I Atlas artificial. That conclusion would be premature, irresponsible, and potentially wrong. The December observations will provide crucial tests. If they reveal natural processes operating in unusual but explicable ways, the exotic theories will rightfully collapse. But it does mean being willing to follow the evidence, to update our beliefs based on observations, to admit when conventional models struggle to explain what we're seeing. Science advances by questioning assumptions, by testing limits, by occasionally discovering that what we thought impossible is merely improbable. The greatest scientists in history were those willing to look at data that didn't fit, to take anomalies seriously, to propose explanations that their contemporaries found absurd. Galileo was ridiculed for claiming Earth moved around the sun. Wegener was dismissed for suggesting continents drift. The existence of black holes was considered mathematical fancy until observations forced their acceptance. 3I Atlas might prove natural and simply unusual. That's the most likely outcome, and it would be scientifically valuable even so. But if it proves something else, if the observations force us towards conclusions we're not prepared to accept, then the greatest scientific act would be accepting them anyway. Because in the end, reality doesn't care what we believe. It simply is. And our job, as curious beings trying to understand the universe, is to look without flinching, to measure without prejudice, and to report what we find, even when it scares us. Conclusion: waiting for the universe to speak. 3I Atlas continues its journey. Right now, as you hear these words, it's moving away from the sun, carrying its secrets, leaving behind a trail of questions and data. In 6 weeks, it will pass closest to Earth. In 6 months, observations will be complete. In a year, papers will be published, debates will conclude, and consensus will emerge. But the mystery it brought with it will persist. Even if every anomaly receives a satisfactory natural explanation, the questions it forced us to ask won't disappear. We've glimpsed the edge of our understanding. We've seen how quickly certainty dissolves when confronted with something genuinely novel. We've discovered that the universe still holds surprises, still challenges our models, still refuses to fit neatly into the categories we've prepared. That's the gift 3I Atlas brings, regardless of its ultimate nature. It reminds us that we're still beginners at this, still learning to read the cosmic story, still capable of being astonished by visitors from the deep dark. The universe is vast beyond imagining, ancient beyond comprehension, and filled with wonders we're only beginning to glimpse. Some of those wonders will prove natural, the product of physics playing out across billions of years. Some might prove something else entirely. InfiniteVoyage will continue following the 3-Eye Atlas story as new observations arrive. Subscribe and join us for the next chapter in this unfolding cosmic mystery. Either way, we get to watch, we get to wonder, we get to stand beneath the stars and know that somewhere out there, answers exist. And slowly, piece by piece, observation by observation, we're learning to find them. 3-Eye Atlas broke 9 laws of comet physics. In the breaking, it opened 9 doors to new understanding. Behind those doors, whatever we find will be truth. And truth, in the end, is always worth the journey. Keep watching the sky. The universe isn't done speaking yet.